Let's continue our transition from differential calculus to integral calculus with the U-substitution for integrals. The last time you did a U-substitution was likely for the composition of functions when you took a derivative. For instance, if y of t equals g composed with u of t, then the derivative of y with respect to t was equal to the derivative of g with respect to u times the derivative of u with respect to t. And notice this was known as the chain rule. We're now going to turn our attention to the U-substitution for integrals. It's going to run similarly to the U-substitution for the chain rule. However, our goal is to anti-differentiate. This is the U-substitution for integrals. A very special note here is that you want to be able to spot g of x living inside another function. And that is going to enable you to make an educated guess on what u actually is. Even though the theorem provides a result, the theorem does not indicate that the result often requires trial and check methods. This means you might not get the right answer on the very first try, but you just got to be persistent in integral calculus. You have to try and try again. This is often known as the first technique of integration. Integrate means to anti-differentiate. These two words are actually synonymous. Why don't we begin with a few examples? Let's make an educated guess of what u is. Does u live inside another function? And now we're going to write this equation in terms of its differentials. Now we have du is equal to the opposite sine of x times dx. Keep in mind your u's and x cannot mix and match. We're going to separate all our u's on one side, and then we have all our x's on the other side of the equation. Balancing this equation, we can see that the opposite of du is equal to sine of x times dx. We are now ready to make the U-substitution. When you make the U-substitution, your integral of x's will transform into another integral of u's. And we could definitely integrate this. How do we know if we have the right family of antiderivatives? Well, we could actually check our answer. Remember, we could actually just differentiate our family of antiderivatives, and we hope to get back the continuous function that we started with. Notice when you check this differentiation, you will need to execute the chain rule. And notice this derivative is in fact this function right there. So this checks. Once you realize you have checked your answer, you are more confident with your work and your U-substitution. I strongly advise you to check with differentiation. Now, if you think you got the hang of this, or you want to try this on your own, feel free to pause the video and try some U-substitutions. And remember, you might not get it on the first try, so you might have to try again. When you're ready to check your answer, go ahead and play the video. A key hint to this entire process is that you can never divide by a variable. If you divide by a variable, that means you divide it by 0, which is a false procedure in algebra. And notice we can integrate this rather easily. Make sure you substitute u back in. And I'll leave it up to you to check your answer. Notice I do all my u-subs off to the side. You might need to draw a vertical line to keep your work organized. du is now equal to dx. However, x is equal to u minus 1. And now we're ready to do our U-substitution for integrals. Notice you have an entire integral with just u's. You cannot mix and match. There should not be any x's after you do your U-substitution. Use your integral properties and continue to integrate. Typically, if you begin with a radical, we can actually finish our answer with a radical. Once again, I'll leave it up to you to check your answer by differentiating your family of antiderivatives. Notice we are ready to make our U substitution. And this is not terribly difficult to integrate. You got to know all your antiderivatives that you've learned in the past. Let's continue to integrate with more examples. The next 4 examples and integrals that you'll see quite often in integral calculus. Remember, we are working on the U-sub for integrals. Feel free to pause the video and attempt this trial and check method on your own. In many cases, you might try a U-sub that does not work at first, and then you might have to start over and try a different U-sub. I like to draw a vertical line off to the side. A side for me is off to my right, and that will allow me to write my U-subs. Remember, we need to write an equation that involves differentials, and those differentials are separated by letter. So usually U's are on the left, and then your independent variable that you started with is on the right. These examples arise so often that you often check it with differentiation. Notice your dx is going to be substituted. And we could integrate this. Let's go ahead and check our family of antiderivatives by differentiating it and see if we get the original continuous function. Notice during your check with these U-substitution integrals, you will have to check with the chain rule. What's the integral of tangent of x times dx? First thing you want to do is take advantage of your expert knowledge of trigonometry. Once you do your U substitution, make sure you proceed with differentials, and they're separated by the equal sign. You will have one letter on the left-hand side, and you'll have the other letter on the right-hand side. The opposite of du here is equal to sine of x times dx. We are ready to substitute. And notice you can integrate this rather easily. Let's go ahead and check this with differentiation. When you check this, you are going to need the chain rule. The chain rule is the derivative of the outside function evaluated at the inside function times the derivative of the inside function. The derivative of a constant is simply 0. Notice this function is in fact the original continuous function that we have. So this checks. Once it checks, you could actually encapsulate all your work here because every step of the way matters. These next couple of examples are very interesting. They look similar, but they're actually extremely different. What do you think the family of antiderivatives is going to be? The U-sub for this is not obvious. In fact, what we have to do is rely on our expert knowledge of algebra. First thing we're going to do is make this look like an integral that we could recognize. And we know a here is not 0. A, remember, is a number, so it acts like a constant. Your only variable here is actually x. We have an easier way to analyze a U-sub here. We're going to write the equation that involves differentials. And we could substitute dx to be a times du is equal to dx. We're ready to substitute everything. Dx is a times du. And then in the denominator, we simply have 1 plus u squared. And we know how to integrate this. Make sure you back substitute your u. And we now have the family of antiderivatives. More commonly, this integral gets used so often that it gets its own formula. Let's look at the next example, which is similar but extremely different. Once again, we'll rely on our algebra to get this looking like something we could recognize. Now remember, b is greater than 0. So 1 over b is a constant. Once again, we could spot a function living inside another function. It makes sense to attempt this U-sub. After you state your U-sub, write your equation involving differentials. And remember, b is not 0 here. We're ready to substitute. And we know how to integrate this already. Like the previous example, this comes up so often that it gets its own formula. The key is that you don't mix these two examples up. You want to practice it enough that you gain confidence and that you are precise and accurate with such formulas.